microwave wet digestion. Three things have to be kept in mind, that when we are analyzing the glass samples, particularly glass sample of the type SRM 621, which is a multi-element composite and which is embedded in the silicates, it needs to have a proper microwave digestion programming. 13 acid mixtures of hydrochloric acid, nitric acid and hydrofluoric acid mixtures have been utilized to be able to completely digest the samples for all the metal contents such as calcium, sodium, aluminum as major components, and in minor components iron, magnesium, barium, titanium, manganese, copper, antimony, cobalt and lead. The analytes were determined using multi-element matrix match standard solution. Obviously, it is always a calibration method. So, the standard also must have all these components to be able to analyze the same metals in the sample. The analytical data matrix was processed chemometrically in order to evaluate the examined protocols in terms of their accuracy, precision and sensitivity, and eventually select the most efficient method for the ancient glass. So, there was some permutation and combination in the method that was developed, and the best method that gave the best analytical data in terms of its chemometric manipulation was the one which was used for analysis of the ancient glass samples or the archaeological samples. ICPAES parameters such as spectral line, RF power and sample flow rate were optimized using protocol which were used in the process. So, these are the three things which were manipulated. The spectral lines, that means which line to choose. The other day I was mentioning, when I was talking about ICP and AAS, I said that in ICP we can do multi-element analysis, and while we are doing multi-element analysis, if the two metals have very close spectral lines, then we choose the second grade of the spectral lines for the second element, so that there is no interferences caused by the spectral lines, and there should not be any confusion, because the two metals may not be able to be discriminated properly. Finally, the optimal method was successfully applied to the analysis of a number of ancient glass fragments. To be able to know what the glass composition was at that time, or what was their methodology to prepare these very different types of glass material which are compared with the modern glass, one needs to understand the composition of these in terms of their metal content. Inductively coupled plasma atomic emission spectrometry, again and again I am telling about these machines in so much of great details, because one analyzer should be able to discriminate what to use and where to use. Inductively coupled plasma atomic emission spectrometry, that is ICPAES, is a widely used technique for the several samples, as it is sensitive, accurate and with low limits of detection. Due to the fact that ICPAES uses mainly liquid samples, an effective and convenient decomposition method is usually necessary. So, now we know that this is a method which can be used for any and every sample, although it is sensitive and accurate and goes up to lower limit of detection. So, therefore, the only challenge that an analyzer or an analyst has to face is to be able to prepare the liquid sample most effectively and most conveniently. if the decomposition or digestion step is very cumbersome or long drawn, then it is not a very good technique and cannot be adapted by every laboratory. Hence, the decomposition method should be very efficient, and that is the most important step, because as I told you, silicate or glass samples are very tough to digest, and unless and until there is a complete wet digestion of these glass silicates, it is not possible to get all the metals extracted into the solution, and unless and until all the metal come into the solution, the analysis can never be exhausted and complete. Destructive processes like wet acid decomposition in open vessels or alkaline fusion are commonly applied to analysis of silicate matrices like ancient glasses. The above decomposition methods, when conventional heating is employed, have some very serious disadvantages like long reaction time, incomplete dissolution of silicate matrix, sample contamination and losses of volatile elements. Many of these disadvantages can be overcome using microwave assisted wet acid decomposition in closed pressurized vessels in presence of appropriate acid mixtures containing hydrofluoric and boric acid, or alternatively HBF4, that is the hydrofluoroboroacid. So, you see that what are the disadvantages if we try to digest these glass samples in open vessels? There are several and very serious disadvantages. That is, firstly, it is a very long process and it may or may not completely digest the silicate, and as what I told you, if the silicate matrix does not get completely digested, the metals that are embedded inside, which are much smaller in quantities or even in sometimes trace quantities, cannot be extracted or digested into the solution, and unless and until they come into the solution, it is not possible to analyze them by ICPAES, and the sample in the open vessel may get contaminated by outside agencies, and sometimes the volatile elements also may be lost, because there is a open vessel and it is getting heated and the volatile elements can go away from the matrix or from the dissolved solution. So, that is why it was important to design a method of microwave assisted wet acid decomposition, because it is carried out in pressurized Teflon vessels, and therefore, because it is made up of Teflon, it does not get affected by any of these acids like hydrochloric acid, nitric acid, boric acid, or even hydrofluoric acid. And sometimes the combination of boric acid and hydrofluoric acid have also been taken into account for the complete dissolution of the silicate matrix. How procedures are developed? See, there is always, I have told time and again, that there is a necessity, and for this necessity there is a new invention. So, similarly, that is how science progresses. When there is no need, there is no science, because everything works on what has been already invented. But every time there is a new type of sample, a new type of matrix, and it is felt that complete digestion has not taken place by the existing method, a new method is developed. The aim of present lecture was to learn about a method for microwave assisted wet acid decomposition of the glass matrix, suitable for subsequent analysis by ICPAES. It was felt that glass, which is the toughest to digest, needs more attention, and therefore, there should be a new method of microwave assisted wet acid decomposition. For this purpose, a number of 13 acid mixtures containing HCl, HNO3 and HF were examined for their effectiveness in relation to two different microwave programs for pressure and temperature. So, the design of the method of microwave is now elaborated. You will see that two different programs were conducted in microwave analysis. Just the way we have cooking recipes, we cook dal in many ways and the sambar is made in another way, and there is some other amti is made in a third way. Similarly, we have microwave assisted programmed techniques for digestion, so that we see which one is better. In the case of food, it is the taste which matters, but in this case it is the best dissolution of all the components which matters. I am giving you this day to day life example only to be able to correlate, although dal has nothing to do with microwave digestion of silicate samples. Consequently, 26 microwave assisted composition protocols were tested to a standard glass reference, that is SRM 621, and this was listed in the NIST library in order to determine the most accurate and efficient protocol for the simultaneous multi-element analysis. The accuracy was evaluated by comparing the mean experimental concentrations with the corresponding certified values of the SRM material. So, repeatedly the different protocols were applied, different methods of microwave acid digestions were applied, and it was found that these out of this method, which are the methods which give consistent result, because the standard reference glass sample SRM 621 has a very finite composition, and so that is taken as a reference standard. So, the first analytical protocol was tested against this SRM 621 glass sample, and then it was used as a reference standard for calibration method for the sample glass samples. In addition, the slopes of the calibration curves were used as a reliable criteria to evaluate the sensitivity, while the relative errors were used to estimate the accuracy of each procedure. So, the whole method was developed. It was a calibration method which was then used for the new samples, whether it is archaeological sample or whether it is modern glass sample, was all compared with the reference sample SRM 621. Acid mixtures. Why there is a necessity for having such combination of acid mixtures? Glass and glassy matrices are difficult to be dissolved by common rapid dissolution processes due to the silicate matrix. Now, if we have suppose a metal or an alloy, it is very easy to digest in an open vessel simply by adding a little hot dilute nitric acid or hot dilute HCl, and the metal will completely come into the solution by acid digestion by merely heating little bit. But that is not the story when we are analyzing silicate matrices or glass sample. Why? Because they have a very complicated structure and a very tightly bound structure. One of the most common approaches involving acid attack of the sample by a mixture of acid definitely containing hydrofluoric acid, or alternatively the alkaline fusion by using sodium or lithium fluxes, was carried out. Now, there have been methods which you may have come across in your BScs and MSc experiment, that metals were analyzed or certain compounds were analyzed by sodium fusion. In place of sodium, even lithium fusion can be taken. That means the compound and a piece of sodium are kept side by side and then it is ignited. In the burning process of the sodium fusion, this gets into solution, and when water is added to this whole charred material, it is expected that all of it will come into the solution form. but that was not a very convenient method. That is why the use of hydrofluoric acid was introduced. In this case studies, various acid mixtures of concentrated nitric acid, hydrochloric acid and hydrofluoric acid were compared to investigate the most efficient combination for the extraction of metal from glass material. So, first a comparative data was created by using only hydrochloric acid, the traditional digestion acid, or by using nitric acid, which is also traditionally used or conventionally used for digestion of metals. But it was found that not all the metal came into solution, and that is why there was an introduction of hydrofluoric acid. But the problem of using hydrofluoric acid is that it cannot be used in glass beakers, because glasses are again made up of silicate and silicates react with hydrofluoric acid. So, then what will happen, that it will digest the beaker also and the sample also. So, that is why these Teflon vessels were brought into picture. And when it was investigated and found that which one is most efficient, the combination of extraction, it was found that the best decomposition conditions were when all the three are used together. In all cases, the total volume of acid in these Teflon PTFE vessels was fixed to 6 ml. It cannot exceed more than 6 ml because the vessels are slightly big, but there has to be a vacuum space to be able to handle the pressures of the gas that are generated out of these acids. They are not all in liquid form, some of them are also in the vapor form, and if the liquid volume becomes large, then the total space that would be left will be small. So, that was kept in mind that these three acids, that is the hydrochloric acid, the nitric acid and the hydrofluoric acid, must be taken in combination, first thing for the glass analysis or decomposition, and also the total volume of these three acids, concentrated acid, should not exceed more than 6 ml volume. Microwave assisted decomposition. Amounts of 0.1 gram of the standard SRM 621 were accurately weighed into high pressure closed Teflon decomposition vessels. Then 2 ml of deionized water and 6 ml of acid mixtures were added carefully. The vessels were gently shaken and sealed. A total of 8 sub-samples were evenly spaced on the microwave turntable. Now, microwave can hold 8 such vessels, and in all the 8 vessels there should be at least water or the samples dissolved in water. The turntable will not work if all the vessels are not fitted, and to have an efficient absorption of microwave and no wastage of microwave energy being taken place, all these 8 Teflon vessels which are on a turntable in a microwave should have water or the sample which is digested with acids and water, because microwave energy only excites the water molecules, and that is how it helps in digestion. The final mixture was diluted to 100 ml. After the digestion had taken place, we can then increase the volume to 100 ml. The vessels were washed with 5 minutes heating in microwave at 1200 wattage in presence of 30 ml of 0.5 molar solution of nitric acid. 2 different heating programs were examined. The first microwave program consisted of 4 stage 1 to 4 and was labeled as A method. The second microwave program consisted of 2 stages 1 and 2 and was labeled as B method. Each protocol was labeled from the acid mixture that was used for the decomposition and the microwave program which was applied. So, 2 different programs were carried out as what I mentioned in the earlier slide, and it was compared which method, whether the method with 4 steps or the method B with just 2 steps, which one is better for the complete digestion of this standard reference glass sample. Optimization of ICPAES instrumental program. The sample flow rate is a critical parameter because it largely determines the residence time of the analyte species in the center of the plasma torch. The higher flow rate, the more amount of sample solution to be atomized into the plasma. Consequently, the analytes which emit strong atomic lines, a fast flow rate might be used. The incident RF power affects the atom excitation according to the nature of the analyte species. The more power is applied to the plasma, the hotter the plasma gets. Consequently, for analytes that require more energy for excitation and ionization, a high power would provide greater sensitivity, while the easy excited analytes at low power would increase their sensitivity. So, here there has to be certain instrumentational manipulation also. I just told you the sample preparation needs manipulation and complete digestion. Similarly, there has to be some parameters that need to be adjusted according to the sensitivity and the presence at which they are in the solution while analyzing on ICPAES. And what are these parameters? The incident RF power that affects the atom excitation will also depend on the nature of the analyte species. More power will be applied for plasma to get hotter, so that the more energy can be provided for excitation and ionization, and greater sensitivity can be attained. The influence of sample flow rate and RF power on sensitivity was studied using calibration curves, which were obtained from 6 standard solutions, varying the sample flow rate in the range of 1 to 3 ml per minute and the RF power between 1300 to 1500 watt respectively. The results of the regression analysis, that is the slopes, indicate that the sensitivity of the determination is higher for RF power at 1500 wattage and for sample flow rate at 2 ml per minute is the optimum. So, these kind of optimization studies need to be carried out to be able to find out. It is not that only one method is designed and the new experiment is carried out on that one method and it is found that this is the foolproof method. Nobody can say that this is the best method unless there is an optimization. When we try to analyze, we need to carry out several methods, and from those several new methods, then the best method is chosen to be used on a routine basis. Sensitivity check and spectral line selection. I have been talking about spectral line selection only when we are discussing ICP. I said that if two elements have close spectral lines, it will not be able to determine whether it belongs to element A or whether it belongs to element B. In such a case, the element A is chosen as it is, and for the element B, another spectral line away from it should be chosen, so that there are no spectral line interferences. The sensitivity of a characteristic spectral line of the analyte is likely to affect by the matrix of the resulting solution after various decomposition procedure. So, what happens when different acids are added, the sensitivity also changes, it does not remain the same. Now, under the given compositional changes, because there is also these acids which are in the solution form, there has to be some other manipulations in terms of selection of the spectral lines. Thus, at this step the best spectral lines should be primarily evaluated according to the overall sensitivity obtained, including for each element only the spectral lines where quantitation was achieved. So, that means that whichever spectral line represents that particular element highly, that should be chosen. So, here again there are some manipulations that need to be done for such a programmed and complicated analysis of glass samples. Following spectral lines such as for aluminum 308.215 nanometer was chosen, for iron it was at 239.521 nanometer, for calcium it was at 317.933 nanometer, for magnesium 280.271 nanometer, for titanium it was chosen at 336.121 nanometer, for cobalt it was at 238.892 nanometer, for lead it was at 261.418 nanometer. Now, you see they are fairly between the range of 308 to 261, but and 233. Different spectral lines for different elements were specifically chosen. The sensitivity for sodium and antimony was practically at the same level for both spectral lines, but a little higher is observed at sodium 330 298 nanometer, and for antimony it was 206.836 nanometer. Now, so that is why, since they were very close originally, two different lines were chosen for sodium and antimony, so they can be separated out and there should not be any confusion whether this line and this concentration belongs to sodium or antimony. Consequently, the above spectral lines were recommended as an optimum proposed method. So, this was finally concluded that aluminum at 308, iron at 239, calcium at 317, magnesium at 280, titanium at 336, barium at 233, manganese at 257, copper at 324, cobalt at 238, lead at 261, and for sodium 330 and antimony 206 were the final chosen spectral lines for this glass analysis. Conclusion: the developed microwave assisted wet acid composition method was proven to be most efficient for the quantitative determination of major and minor constituents in standard reference glass material SRM 621. The investigated method presented good accuracy, precision, sensitivity and also speed and safety as compared to conventional decomposition techniques of glass material analysis. Although the recommended method is referred to as specific sample matrix, it is readily applicable to other glass materials of archaeological origin. That means, it is a method which is not only for reference sample, but it is also meant for modern glass samples and old time ancient glass samples. So, it is a method for all types of glass samples. Complicated and very intricate analytical method has been developed. The use of microwave heating in closed vessel accelerates the procedure and enhances the decomposition strength of the examined acid mixtures. The standard glass SRM 621 was decomposed successfully using acid mixtures, hydrochloric acid, nitric acid and hydrofluoric acid, and a 4-stage microwave program allowing determination of all the examined analytes was carried out. The presence of hydrofluoric acid and nitric acid in the acid mixture is necessary for the decomposition of glass matrix, as what I mentioned. Again and again I am mentioning, because silicates are very tough to analyze and to decompose, and determination of the analytes were carried out, while the use of hydroboric acid in a separate stage of the microwave decomposition is necessary for the dissolution of the produced fluoride salts. So, first it converts into the, when it is reacted with HF, it converts into fluoride, and then the boric acid further dissolves the fluorides. The gradient increase of the power and the pressure during the microwave procedure were found to ensure the most efficient decomposition conditions for this material. The proposed method could be adapted for a multi-element analysis of ancient glass specimens and also can be applied to common modern glass analysis of similar composition. So, it is a method which has been found to be foolproof for all types of glass samples. Then coming to the use of ICP in pharmaceutical and biomedical analysis. As I said, every time there is a new type of sample which has complicated matrix, there is a challenge for the analyst to design a method which should extract all the ingredients, and therefore, only the efficient analysis or data can be obtained. With the development of life sciences, pharmaceuticals and biomedical analysis, it becomes more and more important in medical science to be able to utilize these techniques and to analyze the analyte. Further studies will be hopefully established if it is possible to use inorganic elemental standards or small organic compounds in the inorganic standards and quantitatively be able to determine all the kinds of drugs, nucleotides and sulfur or phosphorus containing peptides and proteins at appropriate concentrations with an acceptable accuracy. Since 1980, inductively coupled plasma mass spectrometry, that is ICPMS, has emerged as a new and powerful analytical technique which is suitable for elements and isotope analysis. It offers extremely wide detection range of elements and co-analysis of most elements in the periodic table. Also, it can be applied to perform qualitative, semi-quantitative and quantitative analysis and isotopic ratios through mass to electric charge ratio, that is with the help of the MS. With the help of ICPMS, the struggle of searching for an excellent quantitation or quantification technique in that examples like drugs and proteomics has become appreciably close to an end. This lecture mainly focuses on the introduction of the application of ICPMS in pharmaceutical and biological analysis methods. Some problems in application and handling strategies are simply presented here. So, how this ICP and the ICPMS can be efficiently used for pharma samples or biomedical samples? What are the manipulations that require to be done? You know the basic in working of ICP and the ICPMS, but there are, just the way we saw for glass samples, some digestion method had to be a new method. Similarly, how to handle these type of sample, we will take a look at it. Inductively coupled plasma mass spectrometry. Since 1980, inductively coupled plasma mass spectrometry, that is ICPMS, which is composed of plasma as a high temperature 8000 Kelvin ionization source with a quadrupole mass spectrometer analyzer as the sensitive rapid scanning detector, and a distinctive interface has emerged as a new and powerful technique for element and isotope analysis. In approximately 10 years' time, ICPMS has progressed from a laboratory experiment to commercial development and widespread analytical application. So, you see over a period of time it has become so popular. This growth is primarily due to the fact that ICPMS offers extremely wide detection range of element and co-analysis of most elements in the periodic table. For example, a wide range of elements in the concentration levels from PPT to ppm level can be measured in a single analysis. So, whether it is parts per trillion or whether it is parts per million, at every range ICPMS can be used. It can perform qualitative, semi-quantitative and quantitative analysis through the mass to charge ratio. That means, if we want to find out whether it is present or not any element, or in what kind of relative presence they are there, or in absolute terms how much of every element is present, all qualitative, semi-quantitative and quantitative analysis can be carried out, and that is because of this mass spectrometer analyzer, which is highly sensitive, and it is the quadrupole analyzer which takes care of the mass to charge ratio, and that is how it analyzes. And it is so versatile that the technique can substitute almost all traditional inorganic analytical techniques such as ICPAES, graphite furnace AAS and flame AAS, etc. in analytical applicability. So, that means for these biological and pharma samples, the only answer for analytical tool is ICPMS, because it can replace all others and it is definitely far more superior. When I was showing you those graphs, I did show you the supremacy of ICPMS. It was far beyond the graphite furnace or the ICPAES, and of course, certainly with the flame AAS, which has no comparison between the other three. ICPMS has been coupled to all forms of sample introduction or separation techniques or for spectral analysis, including the laser assisted sample introduction, low pressure chromatography, high pressure or high performance liquid chromatography, gas chromatography, capillary electrophoresis and so on. So, it can be coupled with every such instrument, and therefore, all the separation or separated components can be directly linked into the ICPMS. As one of the most significant development in analytical science nowadays, ICPMS has been widely used in many industries. The application which was introduced into geological science research at first has rapidly enlarged to other fields including semiconductors, environmental, nuclear, chemical, clinical, research laboratories after 1984, when the first commercial instrument emerged. So, you see now ICPMS has a wide range of application. It can be used for semiconductors, for environmental samples, for nuclear science samples, for chemical science samples, clinical samples and research samples. The principle and construction of ICPMS. The principal construction of modern ICP instrument are basically identical on the whole. There is nothing, no main change. There is a ICP which employs plasma, and that is why the name ICP for its ionization source, and there is a mass spectral analyzer. So, that is all that the machine has, but the standard of introducing the sample, the procedure for using different types of nebulizers, these vary in an ICPMS machine when the sample changes from one to another.